If we're going to use the Riemann sums as a limit as n goes to infinity to calculate an actual area, we're going to need some formulas for sums of some simpler series. So here's some ones that we will use. And again, these are ones that we need to know. Otherwise, when we come up with the n expressions to be able to simplify to an actual value, it'll be very difficult to do. So these are some of the simpler ones. So if we have a sum from k equals 1 to n of 1, well, the series would look like this, 1 plus 1 plus 1. And the sum of that series will just be n. So if I went up to 10, I would have 10 terms, and that would just be 1 plus 1 plus 1, 10 times to give us n. If I have k, well, I'm going to start at 1, and then 2 plus 3 plus 4, etc. Now this is an arithmetic series, and we have a formula for arithmetic series, and that formula will simplify to n times n plus 1 divided by 2. So that's a simple arithmetic series. We can get into a little bit more complex ones with when we have things like k squared. So we're going to sum up 1 plus 4 plus 9 plus 4 squared plus 5 squared all the way to n squared. There is a formula for that, and that formula happens to be n times m plus 1 times m plus 2 all divided by 6. Now it takes a little while to generate this. And in fact, there are ways to go from the n squared to n cubed, and from n cubed to n4, but that involves quite complicated math, so we're just going to avoid that for now. So we're just going to have these formulas to use at our disposal. So we don't need to know how we came up with them, but understand that if we come up with a k, it's the sum of n to k equals 1 to n of k, it's going to be arithmetic series formula. K squared, we're going to use this formula here. So how do we use this limiting process with Riemann sums to find the area under this curve? So this is a linear equation, y-intercept of 2 and slope of 1, and that area under the curve from 0 to 5. Okay, well, let's just make sure we have the answer to start with. So we know that this is a trapezoid. It has a minimum height of 2. The maximum height is going to be, the maximum height happens to be at 7. So we can calculate the area of that. It's going to be 7 plus 2 divided by 2 times the width, which is 5. So I'm going to end up with 22.5 units squared is the actual area. Okay, so we're just using geometry to do that. So how do we apply the Riemann sums and apply a limit to the Riemann sums to get this exact same area? Okay, so we'll first establish that our delta x is going to be our interval width, which is 5, and we're going to divide that up into n number of rectangles. So it's going to be 5 minus 0 divided by n is our delta x. And the height, each right-hand edge height is just going to be starting at 0. And for every k value, we're just going to add a delta x. And the f of that is going to give us the height of this point. And that we're going to use a delta x here of width. And that's going to give us each rectangular portion here. And we're going to take each one of those and we're going to sum them up from k equals 1 to n. And since we want an exact area, we're going to let n go to infinity. So again, if we wanted to just add up the Riemann sums, we would just find out each rectangle and let n be a finite value. But we want the exact value, so we're going to do a Riemann sum. So I need an expression for x. So each x value is just going to be k times the interval width, which is 5 over n. And then, so I replace the x in the expression. I replace this x in the expression with this k expression. And then I have in the blue brackets is my linear function, x plus 2. And then the delta x I'm going to replace with the 5 over n, which is my interval width. And as n goes to infinity, my interval width goes to 0. Okay, so this is my limit expression. So now I need to evaluate this. And I want to find out the actual area. My actual area should equal 22. So this expression should equal 22. So what I'm going to do first of all is I'm going to simplify this expression. So n to infinity. I'm going to keep my sigma. K equals 1 to n. I'm just going to expand out these brackets. So I'm going to end up with 25k over n squared plus 10 over n. Okay, so this is just going to end up being this here. So I'm going to split this up. So I get the limit as n approaches infinity. And I'm going to take the 25 n squared out. Okay, and I'm just going to be left with 25. Now remember that we can establish the value, sorry, 20, not 25, I'm going to be left with k. Okay, so this expression, now remember that this portion here, we have established a sum for that. And we know that k, if I add from k from 1 to 10, it's just going to be 1 plus 2 plus 3 plus 4 all the way to 10. And we're going to use this formula. But now we're going to also let n go to infinity, but we're still going to use that formula. So I'm going to replace that k with that expression. I also have plus the limit as n goes to infinity of, I'm going to factor out the 1 over n from k equals 1 to n of the value of 10. So it's just going to be 10 plus 10 plus 10 plus 10 infinitely. Okay, so that's going to just work out to 10n. So if again we have a constant, it's just going to be equal to n. So in this case, I could factor out the 10 as well. We could just have 1 plus 1 plus 1 plus 1, and that will also equal just n. So this is, in fact, let's do that. Let's factor out the 10, and we'll just be left with 1. And we know that we've established that in our formula. So again, this portion here is represented in a formula. So now I'm going to evaluate those sums in terms of n. So I have 25 over n squared. This sum is now going to be the arithmetic series formula. So n times n plus 1 all over 2. Okay, that's from my formula here. I'm applying that formula. And then for the other part, it's going to be plus 10 over n. That series is just going to sum up to just n. Okay, and we can see that that is going to be this formula here. 1 plus 1 plus 1 plus 1 to n value is going to be equal to n. And then we're going to simplify this expression and apply a limit to it. So I'm still going to apply, I still have n going to infinity. I'm going to end up with 25 n squared plus n over 2n squared plus 10. Okay, and then as in fact, I need to maybe separate this out. I'll separate this out. So I'm going to end up with 25 n squared over 2n squared plus 25 n over 2n squared. So you can see that these are going to cancel out. Okay, here we have an n in the denominator. So when I apply my limit, when I apply the limit, I'm going to end up with 25 over 2 plus 25 over 2 times infinity, since there's still an extra n left over, plus 10, and that gives me the area that I'm looking for, 12.5 plus 0 plus 10. So there's my 22.5 units squared of area. So we needed to break this down into the sigma form, and in terms of n, our sigma form in terms of n, we needed to do some algebra to simplify it so that we can tease out the sigma of k and sigma of 1. We needed these formulas to be able to evaluate it, and once we evaluate it, we can simplify and apply our limit, and we can see that we end up with the exact same area when we let n go to infinity.